Hi everyone, my name is Jia Mu. I'm a senior student studying computer science, data science, and honors math. This is my EECS203 IA application video. Today I'm going to talk about pigeonhole principle. So what is the pigeonhole principle? The definition of the basic or classic pigeonhole principle is that suppose we have n and m are which are positive integers, and we suppose m is greater than n. Then if we want to place m objects into an empty boxes, there will be at least one box containing at least two objects. So this definition is pretty easy to be understood because if we first place an objects in atoms into an empty boxes with each box containing exactly one object, then we will have m minus n objects remaining. If we want to place this m minus n objects into these n boxes, there has to be at least one box containing at least two objects. A more general version of pigeonhole principle is that suppose we have three positive integers, n, m, and r, and we suppose m is greater than n times r. If we want to place m objects into n empty boxes, there will be at least n boxes. There will be at least one box containing at least r plus one objects, or equivalently, there will be at least one box containing more than r objects. This definition is also easy to be understood because by the similar explanation, suppose we want to place n times r objects into an empty boxes with each box containing exactly r objects, then the remaining m minus n times r objects will be left, and if we want to place those objects into this boxes, there has to be one box which containing more than r objects. Finally, the most general version of the pigeonhole principle is that suppose we have m and n which are finite sets, and m's cardinality is smaller than n's cardinality, then there doesn't exist an injective function f which maps from m to n. This definition is correct because if we have such injective function, we will know that m's cardinality is smaller than n's cardinality, which is a contradiction to the assumption we have. So there doesn't exist such injective function. Now, these three definitions are all definitions of the pigeonhole principle, and we want to use the pigeonhole principle to solve a problem. And this problem states that prove that there must be some positive integer n for 13 to the nth power has 01 as its last two digits. So how do we solve this problem by using pigeonhole principle? A natural thought of this problem is that we want to solve the problem. We want to think of this problem from back to front. So to have a 13 to the nth power which has 01 as its last two digits, we know that 13 to the nth power minus 1 has 00 as its last two digits. And in other words, we know that 100 can be we know that 13 to the nth power minus 1 can be divided by 100. And based on this formula, we know that 100 is a divisor of 13 to the r's power times 13 to the nth power minus 1, where r is a positive integer. And we know that 100 is a divisor of 13 to the n plus r power and minus 13 to the r's power. This looks familiar for pigeonhole principle because this indicates that 13 to the n plus r's power and 13 to the r's power has the same remainder if they are divided by 100. So to have this n, which is we have to have two different numbers like r and n plus r. So here's the way we how to solve this problem. So we consider 101 numbers, 101 different numbers, like 13 to the k's power, where k is ranges from 1 to 01. And we want to place this 101 numbers into 100 boxes, which is labeled by R, where R is the remainder of 13 to the k's power divided by 100. So we have 100 boxes because there are 100 dividers, there are 100 remainders, which are 0, 1, and 299. Since we have 101 different numbers and there are only 100 boxes, therefore there must be at least one box containing at least two objects. So suppose 13 to the a's power and 13 to the b's power are in the same box, say R or R1, which means that 13 to the a's power and 13 to the b's power has the same remainder when they are divided by 100. Then we know that 100 can be is a divisor of 13 to the a's power minus 13 to the b's power. Suppose a is bigger than b. Then we can do the same procedure above. So 100 can be divided, is a divisor of 13 to the base power times 13 to the a minus b's power minus 1. Since we know that 13 to the base power cannot be divided by 100 because 13 cannot be divided by 5 nor 2, so we know that 100 is a divisor of 13 to a minus b's power minus 1. Therefore, 13 to the a minus b's power has 0, 1 as its last two digits. So a minus b is the positive integer which we need for this problem. Yeah, thank you.